Trenton Holiday, thanks so much for coming back on to Evolution Soup all the way from your office in New Orleans, Louisiana. You are Professor of Anthropology as well as Interim Associate Dean at Tulane University in New Orleans, a much-loved guest on this channel, having come on to speak about Cro-Magnons as well as genus Homo. So I thought people would enjoy hearing your conclusions on another great interest of yours, the Neanderthals. So, how have you been doing, Trent? Our last two interviews have certainly been popular. That must be very gratifying to you as a science communicator.
Yeah, it's fun actually doing these interviews, and not to be a mutual, what is it, mutual admiration society, but you're a great interviewer. Love talking to you, and I love your guests. Your other guests are great too. I try to keep up with the people you're interviewing. I like that you've been interviewing early stage career scientists lately, as opposed to just dinosaurs like me. And a lot of Southerners lately, I've noticed too. So shout out to people from the American South.
Well, Neanderthals have been covered several times on this channel, but if you were to give our audience an overview of this species, which includes the newest information the science has discovered, what would you talk about?
I think what I would say about Neanderthals is they're still very likely our closest fossil relatives. There's been some talk about the Denisovans recently with regard to the genetics of Denisovans. Was some suggestion in a paper that came out a few months ago that the Denisovans and Homo sapiens are actually sister taxa to the exclusion of the Neanderthals. I'm not a I'm not convinced by their arguments, which were based on morphology and not genetics. So I still think the Neanderthals are our closest relatives. I brought a couple of examples over and I'll use them periodically. You know, they have long, low crania. They've got that chignon or occipital bun, big noses. I'm going to talk about that and the significance of that with regard to cold adaptation later. And their brains are bigger than ours, which I often impress upon our students because one of the things people assume about Neanderthals is that they had small brains. They also, as we're learning more and more, seem to have lived at very low population densities. So we also have Thorin, the Neanderthal that was discovered in Mandrin Cave. And through genetics, we realized that he is more closely related to the Altai Siberian Neanderthals than he is to neighboring Neanderthals, which just goes to show that many of these Neanderthal groups were small and isolated from each other. I'd like to talk a little bit about how that paper came about. So in 2002, Frank Czerny, who is a physiologist, Ted Stegman, who's a old school biological anthropologist, and I published a paper in that journal, American Journal of Human Biology, on Neanderthal cold adaptation, mostly focused on behavior and physiology. And a lot of the physiology, as I'll discuss in a bit, has to be reconstructed because physiology doesn't really preserve in the fossil record. So Bill Leonard, who's the editor of that journal, asked me if I would be interested in, for the 50th anniversary of the journal, doing a recap. What's the state of the art now in Neanderthal cold adaptation? He said I could invite anybody I wanted to invite. So I invited some young researchers who do really lots of complementary aspects of Neanderthal cold adaptation. Kara Okabach and Libby Cogill and Scott Maddox. And they all brought their own talents to it. And it was a real joy to work with them and kind of put this paper together. But, Neanderthals are a Pleistocene species. They're living in the Pleistocene. And I know a lot of archaeologists have recently made the argument that not all Neanderthals lived during glacial periods, and that's true. But even if they were living in interglacial periods in places like Europe and especially Siberia, they're going to have to deal with seasonal cold. And cold, it looks like cold really shaped a lot of aspects of their morphology, and it also impacted their technology as well.
Just recently, September 2025, you and your colleagues published a new paper in the American Journal of Human Biology on Neanderthal cold adaptation. Now, I think that almost everyone can easily imagine our Neanderthal cousins wrapped in heavy furs, fighting their way through ice age winds in search of food. But just how much did this species have to deal with the ice and snow, and for how long?
So, as a Pleistocene species, Neanderthals are going to experience some very intense glacial periods. In the middle and late Pleistocene, for example, they, Neanderthals, or their ancestors, experienced at least 8 very cold glacial periods. Now, these cold glacial periods are punctuated by shorter, warmer interglacial periods like the one we're living in today. And how cold were these glacial periods? The last glacial maximum, which was about 20,000 years ago, temperatures during the last glacial maximum, so the global average, has recently been reconstructed to be about 8 degrees centigrade, which is 46 degrees Fahrenheit for our American friends. And that's a lot chillier than the 20th century average temperature of 14 degrees Celsius or 57 degrees Fahrenheit. So you get an idea of just how cold these cold temperatures were. Now, Neanderthals, they did exist during these interglacial periods as well. During the interglacials, however, because of the places they're living, not so much in say the Levant, that eastern shore of the Mediterranean, but in places like Europe and especially in Siberia, they are going to have to deal with seasonal cold. And how do they deal with seasonal cold? They deal with it through technology, whether it's clothing or pyrotechnology. They also appear to have dealt with it biologically. And we do have what looks to be adaptations to the cold present in Neanderthals. I'm going to talk about the anatomical ones first because those are the ones we can actually see in fossils. And then we'll shift to physiological ones later because the physiological ones, we kind of have to make some assumptions that modern human physiology is similar enough to Neanderthal physiology that we could actually make some guesses as to how they would adapt to the cold. And perhaps genetic data are going to allow us to tease apart what physiology or what physiological mechanisms were present in Neanderthals for cold adaptation. So there is some dispute as to when Neanderthals and Homo sapiens diverged evolutionarily. I tend to think that it's somewhere in the middle Pleistocene. So that's between 100, the middle Pleistocene is between 129,000 and about 774,000 years ago. I tend to think it's going to be on the earlier end of that, maybe around 700,000 years ago. There have been some studies recently, both based on genetics and based on morphology that say perhaps it's even earlier still, like in the early Pleistocene, so 800,000, a million years ago. I find those dates, I'm suspicious that those aren't quite right. I suspect that the actual split is somewhere around 700,000 years ago. But that puts, again, at least 8 glacial periods that Neanderthals or their direct ancestors experienced. Well, the first structures I'd like to talk about, or the first features I'd like to talk about in Neanderthals, are anatomical features, because those we can actually see in the archaeological record. And so one of the features I want to talk about is the nose, and in particular, the internal nose. So if I show you my Pharisee, you can see it's a very wide nose. It's also a very deep nose because the face of the Neanderthal is prognathic, or it projects forward. And then I also have Shanidar 5 from Iraq, um, which has a magnificent nose, if you ask me. The Neanderthal nose must have been something to behold because it is both wide and projecting. Among Homo sapiens, if you tend to have a projecting nose, it tends to be narrow. And if you have a wide nose, it tends to be less projecting. But Neanderthals have the best of both worlds. They have a wide and projecting nose. And the nose is really important physiologically. Uh, in order for pulmonary gas exchange to work effectively, what we need is for the air that reaches the lungs to be body temperature, so 37 C, 98 Fahrenheit. So body temperature and 100% relative humidity. Given that in a cold or an arid environment in particular, those temperatures are going to be lower than body temperature, maybe not here in Louisiana, and the relative humidity is going to be lower than 100%. There has to be warming and moisturizing of the inspired air. And most, upwards of 90% of the warming and moisturizing of the inspired air occurs in our internal noses. In particular, the internal noses of humans are packed with structures, mostly bony. Towards the front, they're cartilaginous, but these bony structures that are covered with mucous membranes, and they're also highly vascularized. So if you think about it, if you've ever had a nosebleed, like on an airplane, it's like just how vascularized your internal nose is. It bleeds and bleeds and bleeds. And that blood flow actually creates heat, or it actually brings heat from the body core into the nose, into these structures. And I'm going to go ahead and show you in just a minute. And these structures, you can think of them as basically little heating elements within the internal nose. And because they're covered with mucous membrane that's producing mucus, not only are they heating the inspired air, but they're actually moisturizing it as well. So if you look at this is one of these exploded model skulls. What you can see is this dark orange in the middle, that's part of the septum. So that's the nasal septum that divides the nose into left and right halves. And there's a little bit of the septum you can see up top. That's part of the ethmoid bone there as well. This part of the septum, this dark orange, that's the vomer, which is one of my favorite bones. It means plow in Latin, and it is a plow-shaped bone. I used to joke with my students that I was going to name my firstborn kid Vomer, and I did not. Um, and then over here, we have these structures that are coming in from the sides. These are called nasal conchae or turbinates. And you can see those light orange structures, those are the inferior nasal conchae. Those are considered a separate bone within the cranium. So it's considered they're each a left and right nasal concha is a separate bone by itself. And then if you look way up top, just on either side of the septum, you can probably only make out the middle ones, but there are middle and superior nasal conchae that are coming into the nasal cavity. They're part of the ethmoid bone, which is that white bone in there, or off-white. And these structures, just think of them as little heating units. They're got the blood flow, all that vascularization coming from the body core. They're and the septum is as well. Septum also is highly vascularized. So the internal nose, when air comes into contact with these nasal conchae or turbinates, as they're sometimes called, it's those structures are going to warm and moisturize that air. And again, 90% of the warming and moisturizing of the air that we breathe in, it occurs in that internal nose. It doesn't occur in the throat, either the upper throat or the lower throat or the trachea or the bronchioles. It's the nose is where the action is with regard to warming and moisturizing the inspired air. Have you ever run across campus, maybe, or to get to your job? You do that in the winter, and you run, and you're breathing through your mouth because you're trying to hurry, and you get to your destination on a cold day, and your lungs start to hurt. Your lungs are hurting because you've desiccated them. You're breathing through your mouth. You're not having all that warmth from those structures, those internal structures, actually warming and moisturizing the air for you. So what was kind of curious, at least for a number of years, and recently people have started to think they've understood it, is it doesn't make a lot of sense for Neanderthals, if they're cold adapted, to have this wide nose. It doesn't make a lot of sense to have a wide nose. A narrower nose, if you think about it, so you have the narrow nose and you have the nasal conchae coming in, and then you have the septum in the middle. That's going to have much higher surface area to volume ratio than a wide nose. All others, if all the structures equal, a wider aperture is going to have more volume relative to the surface area, and it's not going to be as effective at cooling as a narrower nose. And Neanderthals had these wide noses, and so for a long time people were like, well, if they're cold adapted, why are their noses so wide? And it seems that there's some work from people like Todd Yoakley, Scott Maddox, who was one of my collaborators on this paper, Nathan Holton, Bob Franciscus. They've all kind of put together pieces of the puzzle that show us why the Neanderthal nose is wide. And it's a seeming paradox, but it's not really paradoxical in the end. Again, if you remember, I said the Neanderthal face is a projecting face. And what Nathan Holton and Robert Franciscus have shown is that as the face grows and is more prognathic or more projecting forward, there are constraints on the width of the nose, so that a narrow nose is simply not feasible due to these growth constraints in a projecting face like the Neanderthals have. And that the narrow noses we see in Homo sapiens today, and that's narrow across the world. I'm not talking about relative variation relative to climate, etc. Modern humans have narrow noses. That's only feasible because our faces are tucked up underneath our neurocrania, right? We have orthognathous faces. We don't have a prognathic face. And so that lack of forward projection allows for this adaptation of a narrower nose. It's simply not feasible in a broader nose. Now, there are some other possibilities here as well. And a lot of work from those same people that I've mentioned before has suggested that Neanderthals may need this big nose to fuel their metabolically expensive bodies. So Neanderthals weigh somewhat, maybe 25 to 30% more on average than people today. And this is despite the fact that they're a good bit shorter than we are. So they weigh more. They may need more air in each breath to deliver oxygen to the body, to feed their heavier and therefore more metabolically expensive organs. So there was an article by Nathan Holton and colleagues, a couple articles about a decade ago. And what he found is that nasal size, he used a bunch of radiographs that were taken during, I think, the 1960s and 1970s of kids, the kind of research one can't do these days. Hey, you just come in every year. We'll take some radiographs of you. Yeah, you can't get that by RB anymore. But using those data, what he found is that nasal size, nasal internal cavity size, correlates well with body mass, because they took all these measurements on these kids, and that male and female, it's correlated with both, but at puberty, males really their nasal sizes kind of take off, and that's associated with that big increase in body size. And so men end up with bigger noses than women, it looks like, in order to accommodate their bigger body size and therefore their bigger metabolism. And in fact, the changes in nasal dimensions are more closely correlated with overall body size than they are with the rest of the craniofacial skeleton, which suggests that it's really under some kind of selection. And then the last piece of the puzzle that I think is really fascinating. So if you look, and I love showing you Shannon R5 just because I hope you can see that the nose is big. But the one thing that you don't see in there, and you don't see it in La Pharisee 1 either, for that matter, are those nasal conchae. And that's just because they're very fragile structures. They just don't survive very well in the fossil record. Nasal conchae, they're thin bones. Sediment gets in the nose and they get obliterated. So one of the ideas that we had, Ted Stegman, Frank Cherney, and I, back in our 2002 paper, is is it possible that Neanderthals have bigger nasal conchae or turbinates, in which case, even though their nose is wide, they could be, in fact, very, very cold adapted. And there's this Neanderthal, I'm sure you can show a picture of it, Mark, the Altamura Neanderthal from Italy. Yeah, it's a beautiful Neanderthal. It's covered with like stalagmitic growth on it. It's lovely. This specimen is beautifully preserved, but it's irretrievably locked in a flowstone in Italy. And there was an Italian graduate student. His name is Costantino Bussi. And Costantino Bussi had an endoscopic study where he actually put it into the nose, and the nasal conchae are beautifully preserved and they're huge. I mean, they're absolutely huge. They're packed in there. So even though the nose is wide in this Italian Neanderthal, he's got these huge nasal conchae in there. So the surface area to volume ratio is going to be very large. You have a lot of surface area. Again, these are moist, hot tissues, the septum and the nasal conchae, and it's going to be very effective at warming and moisturizing inspired air.
And what about other physical adaptations? Although Neanderthals looked similar to Homo sapiens, there were very notable differences. So, how did this species change their body shape to combat the harsh weather of the Ice Age?
One of the features of endothermic or warm-blooded animals is that they show patterning or trends or clines with geography. In particular, there are these trends were codified in the 19th century by Bergman in 1847 and Allen in 1877. And what Bergman's rule states is that within a widespread species of endothermic or warm-blooded animals, those animals in colder regions will weigh more. They'll be heavier, and those animals in warmer regions will weigh less. They'll be lighter. And Allen's rule states that within a widespread endothermic species, those individuals and populations that live in cold regions are going to have shorter extremities, and those individuals that live in hotter regions are going to have longer extremities. And there's a theoretical explanation, it's not universally accepted for this, that this is related again to a surface area to volume ratio. You hear so much about surface area to volume ratios in biology because they're really critical. So if you think about two objects that are the same shape, for example, a golf ball and a basketball, the golf ball is going to have a greater surface area relative to its volume than a basketball. And if this is an animal that is losing heat through its body surface, then the expectation is that by getting bigger, it's going to have relatively less surface area and it should be able to retain heat better. And conversely, by getting smaller, it should have relatively greater surface area and shed heat more effectively. So being smaller in a hot environment makes sense. Being larger in a big environment makes sense. And then Allen's rule is just about, can we violate the assumption of the same shape and create different relative surface areas by focusing on how much of the body is in the torso versus the limbs. The limbs have relatively higher surface area than the torso, and therefore, if you have elongated limbs, you should be able to more effectively shed heat. And if you have shorter limbs, you should be effectively able to retain heat better. And so I'll just show you. This is School 4 from Galilee, right around Mount Carmel. This is about an 80,000-year-old Homo sapiens individual. And then we have SPE2, which is a Neanderthal from Belgium. That's probably about 42,000, 43,000 years ago. And I think what you can see is that the Neanderthal has a much shorter, and these are femora, by the way, or thigh bones. The Neanderthal has a much shorter femur with a bigger femoral head or ball for the hip. It's a much thicker shaft, and this reflects greater body mass as expected from Bergman's rule. the Neanderthal living in glacial Europe versus the early modern human living in the Levant, the eastern coast of the Mediterranean, which never quite experienced the glacial cold that, say, Europe or most of Eurasia did. And also the shorter limbs of the Neanderthal, reflecting Allen's rule as well. So that's just one aspect of their morphology that seems to be related to cold adaptation. Another aspect of their morphology that's related to cold adaptation is their body breadth. So with regard to body breadth, if you have the pelvis, or the os coxa, so this is the pelvis of Kabara II, which is a Neanderthal. One of the things that struck people in the 1980s about this pelvis when it was recovered from northern Israel was just how long, elongated the pubic bone is. So this is the pubis or pubic bone. It's very elongated. And if you were looking at it without taking into account other aspects of the morphology, you might say, well, that looks like a female pelvis of a modern human, but it's actually a male Neanderthal. And then here is that school 4 individual again. Both of these are males. This is Homo sapiens. This is the Neanderthal. And I think you can see, maybe if I put them side by side, I think you can get an appreciation for just how elongated that pubic bone, the body, and also those rami. So the body, set this down. The body is this part of the pubis, and then the rami, there's a superior ramus and an inferior ramus. Both the body and the ramus are elongated, and that reflects a broader trunk. Neanderthals have a broader trunk, and I think this is significant for a number of reasons. One of the reasons it's significant is that seems to be the plesiomorphic or ancestral condition for the genus Homo. So we have a pelvis that's about 1 million years old from Gona. It's a broad pelvis. And what seems to be the case is that Homo sapiens, with our narrow pelvis, we're the weird exception to the broad pelvis rule. But also, with regard to surface area, Chris Ruff did some work in the 90s and early 2000s where he modeled the human body as a cylinder, where stature was the height of the cylinder, and then biiliac breadth or pelvic breadth was the diameter of the cylinder. And he demonstrated that how wide that cylinder is has a major impact on surface area to volume ratio of the body, much more of an impact than the elongation of the cylinder. And with a former PhD student of mine, Bo Kasabova, she came up with a system for sort of estimating the different segments of the body. And I was thinking that we might discover that it would be a little more nuanced understanding. So we had the segment of the upper limb, we had the thigh as a separate segment, and then the tibia, or the distal, it's actually in anatomy, the leg as a separate segment. And I thought we're going to get a much more accurate view of surface area, and we're going to change the limb proportions of these individuals and see some differences. And what was surprising to us was that when we changed things like the length of the limbs, it had a negligible effect on the surface area to volume ratio of the body. What still had an impact was the breadth of the pelvis. So Neanderthals have this broad pelvis, which also impacts their surface area to volume ratio, and means they have a lower surface area to volume ratio, which should allow them to retain heat better. So another anatomical feature that's often been talked about with regard to Neanderthals are they have voluminous rib cages. And it's not just that they're voluminous, but also the shape of the rib cage is of interest as well. So your viewers probably know that apes tend to have a conical rib cage, and there's a huge debate among paleoanthropologists as to whether australopithecus also had a conical rib cage, or is it more expanded. Homo sapiens tends to have what's called a barrel-shaped rib cage. So just as you would imagine, shaped like a barrel. What that's reflecting, of course, is an expanded upper rib cage relative to apes. And then it comes back and tapers back down, much like a barrel. Neanderthals have what Marcus Bastier and colleagues have referred to as a bell-shaped rib cage, which is kind of neat, which means it has this expansion in the upper ribs, and then as it comes down, it maintains that breadth, kind of like a bell. And I think a lot of what's going on, and they do as well, is you have integration. There's a lot of muscles that run from the pelvis to the rib cage, especially the lower ribs. And there's more of an integration between that wide pelvis of the Neanderthals and that big bell-shaped rib cage. Humans, we have a barrel shape, modern humans, because it's coming back to meet that narrower pelvis. Now, Bastier and colleagues argued that they looked at two Neanderthal rib cages that are relatively complete. Shanidar 3 from Iraq and Kabara 2 from northern Israel. And they found that those ribs are different from people today, but they're closest to people from cold climates. But they suggested, we're not sure this is related to cold adaptation, because these guys are from relatively warm regions. They're not from like glacial Europe or heaven forbid Siberia. And so they suspect that maybe this too is related to the metabolic expense of running a Neanderthal body, that you need greater vital capacity, greater areas or size, volume for your lungs in order to fuel that expensive body. I'm not sure these are mutually exclusive hypotheses. I agree that Neanderthals would need bigger lungs to power their metabolically expensive bodies, but it would also be interesting to see what European Neanderthal rib cages looked like. We don't really have much in the way of ribs from Europe. And especially what I'd love to see are rib cages of Neanderthals from southern Siberia, because maybe they'd be even more voluminous than their cousins in, say, the Levant or in Iraq. So, one of the potential physiological adaptations Neanderthals may have had to cold is what's known as brown adipose tissue. And brown adipose tissue is fatty tissue that has a lot of mitochondria in it. And the mitochondria within it are faulty in the sense that instead of producing ATP, they actually have leaky membranes and they leak protons and they generate a lot of heat. It's a very effective means of heat generation. Now, we've long known that adipose tissue is important in hibernating animals, and it's important in babies. Babies aren't so good at body temperature regulation, so they tend to have a lot of adipose tissue right here. Also, their kidneys tend to have it. But in recent years, and we point this out in the article that was published a couple months ago, we realize that adult humans today have brown adipose tissue activity. And we can see it not only in people who live in cold environments, but actually it seems to be a global phenomenon, which would suggest that this may be, in fact, a very ancient adaptation. In people today, it tends to be superclavicular or supraclavicular, the distribution of brown adipose tissue. A lot of important blood vessels, the carotid arteries, the jugular veins. These need to have some protection, and the brown adipose tissue is a way of warming those vessels up. So it's possible that Neanderthals had even more brown adipose tissue than we did. Maybe the genomics of Neanderthals will reveal that.
Neanderthals, we now know, are much smarter and more innovative than previously thought. Your paper outlines the technological adaptations that the Neanderthals came up with over the centuries to fight against the cold. Trent, what are some of these inventions that helped protect them from the elements?
Well, first of all, we think fire, or we know fire, because Neanderthals have halves in multiple sites where we have Neanderthals. We find halves. In some spectacular contexts, these halves are actually complex. Generally, for most Neanderthal sites, a hearth is just a flat area upon which some kind of fuel has been placed and then set alight. So fire is a critical aspect of our adaptation to cold, controlled use of fire, and Neanderthals had controlled use of fire. and in some cases, relatively sophisticated controlled use of fire. Fire dates, there's controversy about the earliest evidence for fire, as you might imagine, but fire may date very well back to 1 million years ago in Africa. And there's really good evidence for fire at Jokodion, the Homo erectus site, which is perhaps about 400,000, 600,000 years ago. So Neanderthals, we're talking about 250,000 to 40,000 years ago, you would expect them to be using fire. Clothing is something else we expect. We certainly think that they had the ability to wrap skins around themselves, in part because the stone tools that are associated with Neanderthals include a lot of stone tools called scrapers, which could have been used for any number of tasks, but scraping hides is one of them. We also discovered relatively recently tools called lissoirs or burnishers. These were generally made from bovid or cervid ribs. And it's one of those fascinating stories where the researchers showed them to leather workers, modern day leather workers, and they knew exactly what the tool was. It's exactly the same tool that we use today to waterproof and to smooth out hides. And so these burnishers have been found in a number of Neanderthal contexts. And there's even some suggestion that this was a Neanderthal invention. And then finally, I'll mention that the eyed needle, which is usually associated with Homo sapiens, and it may be an invention of Homo sapiens, but the earliest eyed needle is from Denisova Cave, and it's about 50,000 years old. And if you recall, Denisova Cave is a cave that's sort of at the easternmost fringe of the Neanderthal range and perhaps the westernmost fringe of the Denisovan range, and it was occupied by both species. So it's possible that in a place like Siberia, where you're going to experience some very intense cold, that Neanderthals came up with an eyed needle as well for making well-fitted clothing, so to speak. Shoes are another possibility. Eric Trinkus did a study years ago about the muscularity of the lesser toes of Neanderthals. And what he found is in unshod modern human populations, people who don't wear shoes, their lesser toes actually are more muscular. And this was a pattern that he found in Neanderthals. But he said he couldn't rule out a soft soled kind of shoe because in populations that wear like a moccasin or a soft soled kind of shoe, they still retain those muscular lesser toes. Most of the footprints of Neanderthals we have are barefoot footprints, but the vast majority of them are in caves where the cave has sort of the same temperature all year long. When did clothing come about? One of the hints is the split between hair lice and body lice. Body lice need to lay their eggs in clothing. And that split is estimated to have occurred about 177,000 years ago, which would suggest that perhaps among the earliest folks to leave out of Africa were the modern humans who left out of Africa would have been already clothed. It's also possible that Neanderthals and Denisovans had independently invented clothing earlier still. It's always a possibility.
Well, it's been fantastic to have you back on the show again, Trenton, and hopefully we'll have you back on again in the near future. So, what's next for you? What new projects can you tell us about?
So I have an article that's hopefully going to come out soon. The first author is Emily Casanova. She was a colleague, a neuroscientist, and for a long time was next door. There's a university right next door to Tulane, Loyola University, New Orleans. She's moved to St. Louis University in the medical school. As a neuroscientist, she's been interested in autism, and she's been linking it to certain Neanderthal segments. So that article is coming out. I think it's coming out pretty soon. I also am still working with my colleagues in Europe. I'm on the EcoPolice, which is a a great archaeological project in Portugal. We found some human remains that we think are from the Pleistocene, so we'll hopefully be publishing those soon. We're also publishing a lot of the archaeology of the Lys Valley in central Portugal, so I'm still involved with that project and enjoy it very much. And if last time I mentioned I was writing a book on the origins of the genus Homo, I haven't had much time to write on it and or work on it because of my administrative position, but I hope to get back to that. I have to address some critiques from reviewers. Some of these critiques are phenomenal, and I'm like, yeah, that probably will make it a better book, even though they're like, oh, you probably don't need this section. You kind of get attached to things you've written. So I do anticipate being able to work on that origins of the genus Homo book. How soon I can get it done is another issue. But it's been really fun talking to you. I really enjoy our conversations, and thanks for bringing me on again.
Trenton Holiday, thank you very much indeed.
Thanks, Mark. Always a pleasure.